Alright, time for another draftphysics.com, debatephysics.com also, so you should check out those websites, really. Lots of arguments there, but I want to make one here at all. So there's lots of arguments proving kinetic energy theory, 1/2 mv squared, or v squared, as Leibniz put it, is nonsense. It's just made up. It's not true. There is no such thing as a squared velocity. Something like electricity proves it, that you don't square the voltage. I mean, it's not a consistent theory. It's nonsense, blah, blah, blah. Lots of good reasons. So I'm going to focus on one particular reason in this video. And it sort of relates to two kinds of arguments. So I'm going to combine the ballistic pendulum with the thrust argument in space. So if you were in a spaceship and all you could do to navigate your spaceship is throw things out of your spaceship, and you did have the choice of how you threw them out. That is, you could use different devices to shoot them out or push them out, and the bottom line is they go out with a velocity, okay? And it clearly does matter to some extent what device you use, because if you're going to think Newton's third law means anything, you're kind of stuck with at least saying you're going to equalize the momentum. All right, so the simple argument is as drawn here. Let's just make it 1,000 things versus one thing. So you have 1,000 things going 1 mile an hour out one side, and out, should point the other way, 1,000 things going 1 mile an hour, and you have one thing, same thing, going 1,000 miles an hour. So it's the same momentum, and the kinetic energy theory says the one thing going 1,000 miles an hour has 1,000 times more energy. That is, more capacity to move things in the universe. But clearly it doesn't, okay, because it can't move anything. So, I mean, there's lots of ways to break this down. So let's say I had 1,000 more of these things. Obviously, the 1,000 things could exchange their energy with 1,000 things, and the 1,000 things would still move 1 mile an hour, right? If the original 1,000 hit things and gave them, like a Newton's cradle, their energy, all they could do is move 1,000 things 1 mile an hour. And if the one thing, though, if I put that into a pile of 1,000 things, you could sort of understand that the one thing going 1,000 miles an hour could make the 1,000 things go 1 mile an hour. So it does all make sense. Momentum is tidy and neat and clean, and it works really well. And kinetic energy just creates a paradox. So the fact is, you could shoot 2,000 joules out one side and 2 joules out the other side, or 1 and 1,000, okay, per the drawing, and your spaceship's not going to turn. That's what a NASA scientist will tell you. You can't throw light things faster and make the ship turn. It doesn't work. So it's pretty good evidence that if there was such a thing as kinetic energy, it's kind of useless because you can't turn a spaceship with it. Now, the alternative scenario is, well, let's just take the spaceship and, we'll just make it look like a pendulum instead. And what we're going to do is absorb a bullet's energy. Now, can I ever collect the bullet's energy in this pendulum, in this spaceship? Can I turn the spaceship with shooting a bullet at it and make it turn? So I'm going to hit one side of the spaceship with 1,000 things going 1 mile an hour. I'm going to hit the other side with one thing going 1,000 miles an hour. Can I collect the 1,000 times more energy hitting from this side? And the theoretical argument is not without paradoxically breaking all the rules of conservation. Because in this case, there's no reflection. So you're stuck with, well, you have 2,000 joules, okay, but you can't convert that into the momentum without making free momentum. So I can't convert the bullet's energy into momentum, because then I'd end up with more momentum. So every single case, in no case of this experiment ever being done by human beings, have they ever been able to collect more than 2 joules. Now, most of the times they collect like 1.9, okay, because it is a messy experiment. You create some heat, you deform the clay, that's some wasted energy. So yes, you don't get all of the linear motion to transfer as the momentum. but it's a tiny percentage. It's, so you conserve 99%. Let's say you can conserve, let's say 98% of the momentum is conserved, and you lose 99.94% of the kinetic energy. Now, your argument will be is that the kinetic energy is in the form of heat, useless heat, waste heat. So the energy can never be used, but it's there, it's heat. And my counter argument is, well, first you have zero evidence that it's there, okay, that you created 1,999 joules of heat. There's no evidence you did that. And the second argument would be heat is momentum. I mean, you can't make heat without using something's momentum. So heat isn't just a magical thing that happens. It has to happen because something loses its momentum. Heat is like little bowling pins, and your bowling ball has to lose the energy for the pins to move. You can't make heat without using momentum. So how can you make it hot and conserve 98% of the momentum? And you can't. It's impossible. It's silly. Yeah, so that should be the end of the argument, right? I mean, you can't compose this argument, right? You can't tell me that, okay, someday we're going to make a way of catching bullets where we can catch the kinetic energy and use it, because it'll be convertible into momentum. And you're basically just saying, though, your math is telling you you can never do that. Because if you do, you have to break the fundamental conservation law where you can't take 2 units of momentum and create 2,000. And you can't make free momentum. And the only way to capture all the joules is to put free momentum, extra momentum, into the ballistic pendulum. More momentum than the bullet has. So that's what you're stuck with. So you really think that's going to happen someday? Someday they're going to invent a ballistic pendulum that can magically convert the joules of energy into momentum, linear momentum of the object, useful energy, usable energy. That someday you'll create a spaceship that can actually catch the bullet and be turned by it, because the ones we have now can't do it. Nothing can do it. Because it's not real energy, is the simple, obvious argument. It's not that the energy is useless, it's that the energy doesn't exist. All right. So it is that simple. I mean, I guess I almost don't have to draw anything else, do I? Do I really have to? Do I have to explain anything else but to say, doesn't this experiment decisively prove kinetic energy is unviable nonsense? You can't collect it. You can't turn it on. You can't move an object in empty space with it. It can't be used in any way to move anything ever. So why are we even talking about it? Because it's irrelevant energy. It's unusable energy. But the very idea that you're saying it's heat. Well, let's use your heat argument. Let's just say you're saying that, okay, there's 1,999 joules of energy and heat inside the ballistic pendulum. Okay, you've never put a thermometer in there to prove that. But let's say you did in the spaceship. So let's say the bullet hits and it creates heat. Well, wouldn't that heat also, in a sense, be a little bit directional, right? I mean, obviously it's going to be kind of an exhaust. So it would move the spaceship, right? If you had 1,900 joules of heat on the surface of the spaceship, well, then heat does move things in space. But that's not doesn't happen. And let's say I shot the bullet from this side of the spaceship. Then I'd end up with heat exiting this side of the spaceship, right? So the spaceship would turn that way, in obedience to Newton's laws. Heat's leaving this way, so the spaceship would have to go that way. And isn't that the same direction as you shot the bullet? So you could actually make the spaceship turn in the direction you shot the bullet? They're both going in the same direction? Now, that doesn't make much sense, does it? Come on. That doesn't make any sense, right? Can't really happen. All right. So look, it's a nonsense theory, never proven. Again, they haven't, they haven't even gotten past step 1, proving 4 feet dropped 1 foot is the same energy as 1 mass dropped 4 feet. Right, twice the velocity. So they haven't proven a one mass going twice the velocity is the same energy as a four mass going one velocity. And then all the other stuff, 25 times the fuel to go 5 times as fast. Car crashes, nothing. They don't have any evidence indicating this is true. And this is glaring. I mean, these are glaring paradoxes. You have 1,000 times more energy going out one side of the spaceship, and the spaceship doesn't turn. You don't concede that's a problem? That doesn't make much sense? Come on. All right, I suppose I should include the part where I think you're just making a mess of this simple physics. And it comes down to things like pointing an arrow. Okay, you could have the same arrow with the same velocity, the same impact force, and if you put a point on it, a spear, a razor blade, it'll penetrate much further than if you don't. So obviously it matters how you apply energy to something else. And yes, it's just a simple fact that if you hit any chemistry, any physical structure with energy at a certain speed, that structure won't be able to transfer it. And for example, in the case of steel, it has to transfer the energy at the speed of sound in steel, which is like 3 times faster than the speed of sound in air, I think. 4 times, 5 times. It's faster. It's a couple of thousand miles an hour, something like that. So there's a limit to how fast it can transfer energy. And if you try to put the energy in faster than it can transfer it, you'll do damage to the structure. You'll deform the metal. You'll create heat, start melting it, do different things because the structure can't transfer the energy because the velocity is too high. So yes, high velocities can fracture things. They can break glass. They can do different things that look like more energy, but you can know they're not more energy. It's just being applied in a way that allows you to fracture the material rather than actually crush it or break it. So karate people use this principle to break a piece of wood, right? If they hit the wood flat with their fist, ouch, it's going to hurt. All right, they do it with less surface area and quicker. The wood fractures. It can't accept the motion, so the little fibers all just snap, and the piece of wood makes it look like, wow, lots of energy. But it wasn't the amount of energy, it was the fact that you applied it quickly. And again, glass is the easy one to understand that, yes, you hit glass with a quick piece of energy, it'll break, and you hit it, you press on it hard with a force, and it can resist, it can bend, it can accept the energy without crushing or breaking or snapping. So yes, it's okay, that can sort of fool us, but it's physics. You're not supposed to be fooled by something that simple. So it just needs to be stated that yes, bullets will rip through tissue and make a hole and do all kinds of things, and recoiling guns, it hits you, it bounces off, leave a little bruise, not a big deal. And you can understand, though, it's because of the way you're applying the energy, not only the speed at which you're hitting a surface, but over how much surface area you're hitting a surface. And if you make the two things equal, that is, you use a lever or some other mechanism to increase the speed of the impact. So if we take the recoil of the gun and we magnify the speed of its force, a few times using a lever, and put a little point on it, well, all of a sudden it's more of a weapon, right? If the recoil of the gun hits a lever and it now moves a pointed arrow 5 times the velocity, it's pretty certain it can poke a pretty good hole in you. All right, now it's still not a bullet, but it's going to get a lot closer. And you can understand that, that's really the argument here, is you just have to understand that, it all converts to the same thing. So I can make the next argument. I might as well make it. I might as well say all I can say on the subject. All right, so this sort of goes back to the joule argument. So it is kind of curious that in the 200 years since joule, I mean, it's like 200 years, I think. 1850. No, well, no, okay, it's almost 200. Anyway, why don't we make a vacuum chamber with water in it and shoot things into it and see how much energy they have? Why don't we do that? So he figured out a way that's pretty reliable in terms of it's pretty consistent how you can heat water with motion, but they don't do it. So they don't make a modern version of Joule's experiment. Just imagine, if they spent $1 million, how good a energy detecting device they could make. And so then we could do the simple experiment: shoot the bullet into the water and let the water have enough water so the bullet will stop moving, and the recoil of the gun, and let's see how much energy, how much water they heat. So I can illustrate that as just this simple argument. So you could imagine bowling pins, or you could imagine anything you want. So we have 100 things, and we're going to put the recoil of the gun into a closed system, into those 100 things, and the gun's going to stop moving, and the bullet will stop moving. And what do you think you're going to get in terms of the motion of the things you hit? Do you really think the bullet's going to cause 1,000 times more motion? I mean, it's a simple. We're going back to the bowling pin, bowling ball argument. There's no logical way for you to take the 8-pound bowling ball going 16 miles an hour and the 16-pound ball going 8 miles an hour and diagram the exchanges of their energy with the pins, and then prove that the 8-pound ball made pins move more. They have to move the same amount. They can only exchange momentum. As pointed out by the ballistic pendulum, the only way you can collect kinetic energy is this heat. You can't move the pins, it could only make them hotter. So you could make the pins hotter, but you can't move them, because if you move them more, you'd have to show where the ball hit and gave more kinetic energy to the thing than it lost. It lost, say, 20 units of momentum, and it gave the pin 22 or 25. You can't make free momentum. It's sort of amazing, I have to say that. But apparently I do have to argue that point, that you're really not going to show a credible experiment where you can make free momentum. Alright, I suppose it's worth emphasizing that you really don't think heat is momentum, and that you have to use something's momentum to make heat, to make atoms move and vibrate. You don't have to use something's momentum to do that. So in the case of the ballistic pendulum, if there's 1999 joules of heat in the ballistic pendulum, what momentum caused all that heat? Because obviously it only had 2 joules of momentum, 2 units of momentum, however you want to describe it. It had 1,000 times insufficient amount of momentum to be able to create that heat. So again, it's creating free momentum in a sense. It's how do you account for something's motion and still even be consistent with what Richard Feynman said. I mean, Richard Feynman, uses this kind of a childish analogy, but he metaphors nature as a child hiding blocks in the playroom, and the blocks can't be destroyed, and they can't make any more, and all you can do is hide them, and all you can do is find where they are, but there's always the same number of blocks in the room. So you're saying that something comes in with 2,000 blocks, that it makes 2,000 more blocks move, it exchanges its energy, and yet all you get out is 2. That 1,900 of the blocks are missing. Can't find them. And like I said, if you claim their heat, then you have to say, oh, it started with 2,000 of something else, momentum. And it didn't. It only had 2 units of momentum, 2 blocks of momentum. Anyway, so not stated perfectly, but again, how can you, how do you physically understand the exchange of energy as something other than momentum flowing from one object into another object? How can you understand any other way? I don't understand how you are understanding it. Right, so another example. Okay, so let's say you do pay some attention to this karate stuff, okay? There's people that will take cinder blocks and they'll put little spacers between them, okay? Or even just pieces of concrete, little spacers between them, and they'll be able to break all of them with a force. And the simple argument would be is that if I put all the blocks without the spacers, and I have another set with the spacers, and I drop exactly the same weight on the 2 stacks, the fact is we know it's the same energy going to be hitting them, and the results will be dramatically different. You know, in one stack I crack 1 block, that's it. The other stack I crack 10 blocks. So it looks like more energy, right? It looks like. But like I said, if you're doing this physics thing, this intelligent thing, you understand the variables. You understand that you've changed the circumstance and you're changing how they can receive the energy. And if you change how it can receive the energy, it can look like more energy. There's not more pieces of concrete moving. There's not more energy. It's that it's dissipated in a way that looks like it's doing more. So again, it's like something can be, you can push something into a circle and it can spin, or you can push something and let it roll, and it, rolling looks like it's, more something's happening. The spinning isn't, doesn't look like anything. I mean, you can understand that it's, you shouldn't be fooled by superficial, appearances, that you have to look a little deeper and think a little deeper about what is actually causing the effect, and that the effect is often being caused not because of what you're putting in, but because of the shape or structure you're hitting. All right. So that's probably enough. I mean, a pointy arrow thing, I've done enough of this. It's disappointing that, yes, you've been fooled by, superficial carnival tricks. So, I mean, I could bring up the Deschardelet experiment, dropping round objects, denting clay, not penetrating clay, just denting it with round objects, and why that's theoretical crap. And physicists should all agree, yes, that's physics. That's not a good linear experiment. It's not linear. And yeah, so I'll probably make a video about the rolling cart thing, just because of the, the little metal wheels on the plastic cart, when it should be a metal cart with plastic wheels. Anyway, it's just it's such rotten logic, reasoning, evidence. It's such bad science. It's just a religion.